أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله وبركاته. Today we will be looking at question 6 of the prelim paper of 2022 which we wrote recently. So question 6, let's just write down our notes. Let's write down in our notebook. Question 6. Okay, let's look at our question. We see that a question that we have is relating to our the KC method, and we'll read the question 6.1. The balance equation below represents a reaction that reaches equilibrium in a sealed container. Yes, so we've got equilibrium. N2 nitrogen plus H2 hydrogen gives you a reversible reaction, equilibrium, ammonia 2NH3, and delta H is less than 0. Now when delta H is less than 0, you should write down here next to it exothermic. I don't think I can write there. Write here exothermic next to it. So you know that the forward reaction is exothermic. Now that we know that the forward reaction is exothermic, let's look at the question. To increase the yield of ammonia, adjustments are made to the temperature, pressure and concentration of the equilibrium mixture. The graph below represents the results obtained. So here's a graph, time, concentration versus time, and we see we've got the three reactants and products. We've got a nitrogen, hydrogen and ammonia. So from 0 to T1, what can we see is that they're all in a straight line, so they're at equilibrium. However, at T1, we see there's something that happened. We see that N1 jumped extra. There's an extra jump to N1. And N2 and N3 bent in a certain way. Then in T2, we see that all three of them have a jump, an increase or decrease, whatever the case is. In this case, it's an increase. And then we see that something happens, and at T3, we just see there's a change where certain ones go up and certain ones go down. So we'll have to analyze that. So the question is, identify the changes made to the equilibrium mixture at each of the following: T1, T2, and T3. And what do we know? The adjustments are made to the temperature, pressure, and concentration. So where's temperature, pressure, and concentration in this graph? So if you look at 6.1.1 T1, what happens at T1? We see at T1 there's an increase in N1, and then there's an effect after that. The N2 and NH3 stay the same, but there's an increase in N1. So we can say at 6.1.1 at T1, what happened? Nitrogen is increased. So nitrogen is increased. So looking at this, we can say the concentration of nitrogen increased at T1. So we must write that down in our answer. So we write on 6.1.1. If you look at 6.1.1, let's write it down. 6.1.1, we can say the concentration was affected, right, of nitrogen increased. Then 6.1.2, so if you go to 6.1.2, what happens at 6.1.2? So at 6.1.2, what happened? We see that all three of them increased. So if all three of them increased, then usually that got to do with an increase in pressure. Because if there's an increase in pressure, then for a short while all the concentrations increase, and then according to the Chatelier, they can again rearrange themselves to create a new equilibrium. So at T2, we can say the pressure increased. T2, the pressure increased. And then 6.1.3, let's see what happened at 6.1.3. At 6.1.3, we see that there was a change, so that the solid line goes up, nitrogen went up, and hydrogen went up. And we can see that the ammonia went down. So that means what happened is the hydrogen and the nitrogen was favored and ammonia went down. It lost out. So basically, according to this, we see that the forward reaction is exothermic. So by basically the forward reaction, an exothermic reaction is favored when there's a decrease in pressure, in temperature. There's a decrease in temperature. But we see that an increase in temperature, because the forward reaction is less than zero, the forward reaction is exothermic. An increase in temperature will favor the reverse reaction, the endothermic reaction. So we see here that nitrogen and hydrogen were favored, and our ammonia went down. So we see that the reverse reaction was favored. So the endothermic reaction was favored. So we can say at 6.1 at T3, the temperature was increased. You can see the temperature increased. 6.1.3. So we've got our 6.1.1 done. Let's look at 6.1.2. 6.2. 6.2 says state Le Chatelier's principle in words. As we said, you have to learn your definitions. You shouldn't lose unnecessary marks for definitions. So this is an equilibrium question. So 6.2 we can say, learn your definition of Le Chatelier's principle. We can say that when an equilibrium in a closed system is disturbed, when equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium. It will adjust in such a way that the new equilibrium will reinstate a new equilibrium by favoring the reaction which opposes the stress. The disturbance or the stress. Okay, so that will be 6.2. Next question, 6.3. The pressure of the reaction mixture in 6.1 above is disturbed by increasing the volume of the container. If you increase the volume, then you decrease the number of moles. you increase, or whatever. Let's get back to this. The pressure of the reaction mixture in 6.1 point above is disturbed by increasing the volume of the container. Alright, so if you increase the number of the volume of the container, then you increase the number of molecules to compensate that increasing volume. So how will the change above affect the yield of NH3? Rather than only increase, decrease, or remains the same. So what we are saying is that if you increase the volume, you go to the reaction that has more moles or more molecules. So if you look at this here, we see that the number of the balancing number here is 1 and 3. So the left side, the number of moles is 4, and on the right hand side, we've got 2. So that means there's 4 on the left and 2 on the right. So which reaction will be favored? The reaction that has the more number of moles. So we'll say, how will the increase above affect the yield of NH3? The reverse reaction is favored, so the NH3 will decrease. 6.3.1. 6.3.1. The yield of ammonia will decrease. 6.3.2. So the question 6.3.2 is, use the Chatelier's principle to explain the answer for 6.3.1 above. So that's 3 marks, right? So we have to state the disturbance first. What is the disturbance? 6.3.2. The pressure will decrease. Because we increase the volume, right? By increasing the volume. Then we can say, according to the Chatelier's principle, the system increase and increase in the number of particles. Thus, the reverse reaction is favored. Right, we can say the concentration of N2 and concentration of H2 will increase, and the concentration of NH3 will okay, that's 6.3.2. 6.4. 5 moles of N2 and 5 moles of H2 are now sealed in a 5 dm cube container. Equilibrium is reached at 440 degrees Celsius. Upon analysis of the equilibrium mixture, it is found that the mass of the NH3 at equilibrium is 20.4 grams. Calculate the value of the equilibrium constant at 440 degrees Celsius. So we must work out the Kc value. So to do that, 6.3, we can make the 6.4. So basically at equilibrium, the number of moles at equilibrium of what was given to us, let us have a look. 20.4 of ammonia is given. Right, so if we must work out the number of moles we got a mole table, so we work out the number of moles of ammonia. So if we work that out, number of moles of ammonia is equals to actual mass over molar mass. And the actual mass of ammonia is 20.4. And the molar mass of ammonia is 17, which gives us, if we work that out, 1,2 moles. Alright, so now let's put this in our table. We got the number of moles that are given, so that we don't need to work out with the X method. The things are given to us. Initially we got 5 moles of ammonia, 5 moles of hydrogen, and at an equilibrium we've got 1,2 moles of ammonia. So let's write this down. So we can say just change this table. This table is not looking good. Just get rid of this table. So we have to draw a table. So we have a table. We insert a table. A table with how many rows? 1, 2, 3, more or less 4 rows. 4 rows. And then we should find one with 6 columns, more or less. Insert, right? So here's our table. So we know we've got N2, N2, H2, and H3, right? And we know that this is the reactants and this is the products. I'll just put a line here. The one goes up and the one goes down. Just for us to see difference between reactants and products. Alright, and we can just say our ratio here. Let's just write something. Doesn't have to be, the table don't have to be exactly like this. So we got 1:3:2. 1, 3, 2. 1 ammonia reacts with 3 hydrogen to form 2. 1 nitrogen reacts with 3 hydrogen to form 2 ammonia. Right, so initially what do we have? Oops. What cannot happen there now? I have to start again. Sorry about this. Oh, there's it. Initially, I have what? Ratio, what do I have initially? Initially, what do I have? How much was used? How much was formed? And then at finally, what do I have at equilibrium? And then we must find out equilibrium and concentration. And then we work out our concentration. Okay, my table went in a mess. I don't know if I must make another. Let's just see if I can salvage it somehow. Oops, that's a bit of a mess. So you draw a nice table, not like mine. And you can work it out. Let's just see. Okay, so we can use this to work out our system. Okay, I'm going to leave it at that. So initially, what did we have? Initially, we had 5 moles of nitrogen and 5 moles of hydrogen. Let's write that down. So we put 5 moles of nitrogen, 5 moles of nitrogen and 5 moles of hydrogen. 5 moles of nitrogen, 5 moles of hydrogen. There's no ammonia at the beginning. When we worked out the number of moles at equilibrium, we saw that there was 20,4 grams of ammonia. So if we worked it out, we can say the equilibrium of ammonia at equilibrium is 1,2 moles. Okay, so what do we notice is that once we've got the initials and we got something at equilibrium, we can work out the ratio and we can work out our equilibrium using the table method. So going further, if we look at this, once we've got this, what can we calculate? So once we know this, we know that once we know we've got this 1,2, it makes a big difference because now we can calculate something. We can calculate there was no ammonia at the beginning and there was 1,2 at equilibrium. So now we know the number of moles of ammonia that were used or formed. So it was the product, so it was formed is 1,2. So we can write this as 1,2 moles of ammonia that was formed. And once we know the amount of ammonia that was formed, from here we can use our ratio. We can use our ratio. If this was formed, we can say 3 is to, there's 2 ammonia formed, there's 3 hydrogen, and there's 1 nitrogen. Right? So if you work it out, if you work it out carefully, we can say if this was 1,2 and that was 2, so we can work out the ammonia, then if this will be work out to 1 is to 3 is to 2, then this will be, if this was 1, then this will be 0,6. And this was 3, that will be 1,8. So we can use that to work out the number of moles used and the number of moles formed. So 0,8, 0,6 moles of nitrogen were used, 1,8 moles of hydrogen was used, and 1,2 moles of ammonia was formed. Now we know that how much we had and we know how much was used. We can see how much we'll have at equilibrium. If only 0,6 was used and we had 5, then at equilibrium this will be 5 minus 0,6 will be equals to 4,4. Similarly, if we had 5 hydrogen, 1,8 was used. If we subtract it, we see that we can get 3,2 hydrogen. Right, now we know how many moles we've got at equilibrium. And we know the container is a 5 mole per dm cube container. Let's just see, 5 dm cube container here. 5 moles of nitrogen and 5 moles of hydrogen are sealed in a 5 dm cube container. So now if we got the moles, and we got the volume, we can work out the concentration. So if you work out concentration is equal to number of moles over volume. You don't have to do it here, I'm just going to put it here just for our sake. Number of moles over volume, and your number of moles are 4,4 divided by 5, and if you work that out, take a calculator and work it out, you'll see that it gives you 0,88. So that's going to give you 0,88. Let me just put that down, take this whole thing out. It's going to give you 0,88 moles per dm cube. Similarly, if you take 3,2 divided by the volume 5 and you work it out, you'll get 0,64. And if you take 1,2 divided by the 5, you get 0,24. 1,2 divided by 5, right? And then if you work that all out, we've got our concentration. We can use this to calculate our Kc now, right? And what do we know about Kc? Kc is equals to the concentration of the products to the power of the products. The concentration of the products will be nitrogen NH3, concentration of NH3 to the power of, that's important, concentration of NH3 to the power of NH3. Concentration of NH3 to the power of NH3. Now how do we work out the power? It will be the ratio to the power 2. To the power 2. NH3 let's just write this properly. Terrible. Kc is equal to the concentration of NH3 to the power of NH3 all over the concentration of nitrogen to the power of the nitrogen, and the concentration of the hydrogen to the power of the balancing number of the hydrogen, that is 3. Let's just double check that. N is 1 and H is 3. N is 1 and H is 3. That's correct. Right, now what we can do here now, we can work out our Kc value. We know that the concentration of ammonia is 0,24. Write it down. Squared. And then your concentration of your nitrogen is 0,88. The concentration of the hydrogen is 0,64. 0,64. 0,8, 0,64 cubed. Don't forget all those squares and cubes, because that's what's going to lose you unnecessary marks. So if you work this out with the calculator, 0.24 squared divided by 0.88 times 0.6 cubed, you'll get 0,25. 0,25, and Kc doesn't have a unit. So from this here we can work out the Kc as 0,25. Okay. So that will be the answer for the Kc value. Calculate the value of the equilibrium constant, so that will be 9 marks. Right. The temperature is now increased to 700 degrees Celsius. What will happen to the value of the Kc at this temperature once a new equilibrium is established? Write down remains the same, increase or decrease. So if you increase the temperature, we see that the reverse reaction was favored, right? So that the number of products goes down, the NH3 will go down, so basically your Kc will decrease because equilibrium shifts to the left. then this will be question 6.5. This was 6.4, 6.5. So the answer will be decrease. 6.5. Okay, so is that the whole question that we've done? 20 marks, a very important question to learn. One of the ways in which they can ask you KC is by a graph, but not always by the graph, but you should know all the systems. You should know delta H is less than 0. What does it mean? Temperature KC definitions, don't forget. Yes, so that will be the answer to question 6 from our preliminary exam relating to KC value.